It's my pleasure to announce the first lecture of the morning by Nicolas Orantan. It's called Quantization of Spectral Curves to Topological Recursion.
Thank you. So first of all, I would like to thank the organizer for giving the opportunity to give this lecture. I hope it will be helpful for at least some of you here. It will follow a bit the lectures of Bertrand from last week. So for those who have seen it, or those who have not seen it, I will recall just a few things. So the topic of this lecture will be a quantization of spectral curves by topological recursion. So can you read it? Yeah, on the camera as well. Okay. So let me begin with a short introduction using the Airy curve, which was studied quite a lot as far as I could hear last week. So last week you've seen different lectures. In two of them, you've seen application of the topological recursion for solving problem of enumeration. And in Bertrand's lecture, you've seen another property of the topological recursion, which is that it can be used in order to quantize spectral curve. What do I mean by that? What Bertrand showed you is that if you start from the simple curve y squared is equal to x, so you define a curve in C2 by this equation, then the topological recursion produces for you some function which we will call psi, a function of x and h bar, a formal parameter, such that it is solution to a differential equation of this form, h bar squared d2 over dx squared psi of x h bar is equal to x times psi of x h bar. So this tells you that not only topological recursion starting from this curve allows you to recover intersection numbers, so problem related to algebraic geometry, but you can build a generating series for these numbers, which are solution to a differential equation of this form. And this differential equation, I'm saying that it's a quantization of the spectral curve I started from, because one way to write it is to say that you could trade your original curve y squared minus x equals to 0 to y hat squared minus x hat acting on psi x h bar is equal to 0, where y hat and x hat are operators acting on psi, with y hat being just h bar d over dx, and x hat being just the multiplication by x. From this point of view, this differential equation can be seen just as a quantization of the original spectral curve, where you replace your function y and x by operator acting on psi. And these two operators, y hat and x hat, they do not commute, which is in contrary to what you had before. The commutator gives you h bar. And that's the reason why we talk about quantization of this spectral curve. Is it clear for everybody? Yeah. OK. So before I go further, I just want to mention something else related to this curve, which is that this differential equation here, you can linearize it pretty easily. In this case, you can obtain it by looking at a linear system of size 2 of this form, psi 1 of x, psi 2 of x. Yeah, and this depends on h bar everywhere, sorry. where L of x is a 2x2 matrix, which has a very simple form, 0, 1, x, 0. So if you look at this differential equation, the first line just tells you that psi2 of x h bar is equal to h bar d over dx of psi1 of x h bar. And the second line of this equation tells you that h bar d over dx psi2 is equal to x times psi1. So it means that psi1 is solution to this equation. So that's what I'm saying, that here I've got a linear representation of my differential equation. And just to make the link with the name spectral curve.
Can I ask you a question? Yeah. So for me, normally quantization, I start from some Poisson structure, yeah. Okay? So in this case, I would have to say that what you're really doing, you have this spectral curve, you probably have fixed some divisor, and then you built some Poisson structure, or in Darboux coordinates, so that y and x satisfy the standard
Poisson structure where? On which space? Because when I'm thinking about such problem, the Poisson structure I have in mind is the Poisson structure on the space of...
but that's the quantum one.
Sorry?
That's the quantum one, yeah. Right? So that's what I'm saying, that essentially you're thinking about y and x as Darboux coordinates, right?
That's what, yeah, when you want to quantize, yes. Yeah.
Yeah. Okay.
Yes, but yeah, just let me mention that at the end of the day, what we're using a lot is not this, this Poisson structure. What we're using a lot is the Poisson structure on the space of SL2 matrices in this case. Okay, so in this case, we have a very simple case, which was presented by Bertrand, where the spectral curve has genus 0, and basically the genus corresponds to the dimension of the symplectic space you use in order to quantize. And so in this case, it has dimension 0, so it's a very simple case. Olivier will present what happened in a more general case, and he will present Darboux coordinate on this space. But indeed, what you would like to have eventually, and that's not what we're doing, is to have a Poisson structure in the space of x and y in order to quantize. But that's not what we're doing. Okay. So we've got this representation here, and just to mention the fact that now, where does this y squared is equal to x come from? You just look at the characteristic polynomial of L of x. So the spectral curve is basically the locus of eigenvalue of your matrix L of x. Now, this case is very simple. It is coming from the fact that we've got a genus 0 curve to start with, and this is the reason why this matrix L of x is very simple and is basically independent of h bar. You will see later in the lecture what happens when the curve has higher genus, and that's one of the big complications that can occur. Okay, so now this was this nice airy curve case, which has been studied from many different points of view. And now there is a conjecture which is there, I think, since the topological recursion was built, I guess motivated more by the matrix model perspective. Bertrand, I think you had it from the beginning, which is that this quantization procedure, you could do it actually for any algebraic curve. Meaning that if you start from an algebraic curve E of xy is equal to 0. Maybe not the airy curve, but maybe not even an hyperelliptic curve, it is believed that the topological recursion allows you to build some wave function psi depending on x and h bar, as in this case, such that it is solution to a differential equation of the same type obtained by quantizing x and y, where now, if you start from, let's say, a polynomial e, you get a family of polynomial which now might depend on h bar, and you want it to be such that e of 0 x, y is equal to your original spectral curve. So there was this conjecture basically stating that using topological recursion, there is a way to build a wave function which is solution to a differential equation obtained by quantizing the original spectral curve. So here there are many things which are not precise at all, in the sense that I don't tell you how I build psi. So for example, here you had one way to build psi in this case, which was a genus 0 case. In the higher genus case, it's going to be much more complicated. I don't tell you what kind of property I want for E. In what I will present, you will see that one of the properties I will have is that I don't change basically the pole structure of my original spectral curve. So from an integrable system perspective, it means that I'm staying in the same integrable system. And I want that the h bar goes to 0 limit recovers the original curve. So going to a classical limit from this quantized case, you go back to the curve you started from. OK, so this was a conjecture which was there for a long time. And it has been proved in many cases, case by case. And then the first kind of general proof which appeared was a proof by Bouchard and Hénard, when the spectral curve defined by E of x, y equals 0 as genus 0. So it was the first general proof, which was already something quite big, in the sense that if you start from any algebraic curve of this type where the genus is 0, then you can quantize it using the topological recursion. There are many ways to quantize it, many ways to define psi, for example, and they studied a different way and how, what different differential equation you will get. So you get different orderings, because you see you start from a polynomial in two variables, where the two variables commute. So when I quantize it, I've got two non-commuting variables. So there might be some ordering issues, different choice of ordering. And in this paper, they study how you can change the ordering by changing the definition of your wave function. Now, going away from genus 0 is quite a big issue. I mean, it was known from the beginning, I think, from the matrix model perspective, that the wave function which is working for the genus 0 case is not enough for working in the higher genus case. The wave function used for quantizing the genus 0 case is such that the logarithm of psi is basically a series in h bar. If you try to do something like that when your spectral curve has higher genus, this is not working. What you need are functions of h bar for psi, which are much more complicated, which are some kind of trans-series. And this makes that all the proof for getting a quantization is much more complicated. And the first proof of this conjecture for a genus 1 case was provided by Iwaki, who proved it for elliptic curves, meaning curve of this form, y squared is equal to x cubed plus ax plus b. So this is, let's say, a particular case because it's just one family of spectral curves. But it's really important in the sense that it is the first time where a genus 1 curve was quantized using the topological recursion. This opened the way for considering any hyperelliptic curve. And this was done independently by Bertrand and Elba. And Olivier and myself for hyperelliptic curve. So curve of the form y squared is equal to q of x, where q is a rational function. Yeah? Yeah.
Would you just repeat what Iwaki did?
Iwaki did quantize this curve, this family of curves. So it's a very specific type of hyperelliptic curve. Its y squared is equal to x cubed plus ax plus b. Now what we did is, instead of having just a cubic polynomial, we can consider any rational function of x.
And Iwaki can do it for any genus, yes?
So this curve has genus 1.
Oh, I see.
Okay? So this is a torus. Now if you consider, so for example, if you would consider here a polynomial of degree 5 or 6 for q, you will get a genus 2 curve. If it would be a polynomial of degree 4, you get a genus 1 curve and so on. So in our case, we can consider arbitrary genus. And so from the integrable system perspective, this corresponds to studying systems of higher and higher dimension. And finally, we joined together in order to prove the conjecture for any algebraic curve. So the four of us last year, we proved it for any, there are some genericity condition, but basically it's for any algebraic curve. So the proofs of this conjecture, actually, if you look at it, it's not that, it doesn't use very complicated tools, but it's quite a lot of computations. So I will definitely not show you this. What we will show you today with Olivier is this part. We'll consider a rather generic hyperelliptic curve, and we will show you one way of quantizing it using the topological recursion. Yeah.
Just do you hope to find the same kind of result for not algebraic curves, like for, yeah.
So, yeah. So here I'm just talking about algebraic curve, and in particular curve in C square. So maybe what you have in mind are curve in C star square.
Well, when the spectral curve is not even a curve.
What do you mean, not even a curve?
Like when you just have some germs of functions and this kind of stuff, and there is no.
Ah, no. Okay. This I don't expect. So okay. If you think of germ of function above the branch points, you mean?
Yes.
Okay. So you see that when I'm talking about that, I'm kind of using function x here, which is a coordinate in a base curve. So what I'm looking at is a spectral curve which is a cover of P1. So here it will be a double cover with a bunch of ramification points. And basically, X is this covering map. If I don't have a kind of global picture, I don't even know how to define this.
I just want to,
But it's a good question, so something I will not present here and which has not been proved is what happened, for example, if instead of having a cover of P1, we would have a cover of a torus. So this generalization would correspond to having, for example, some X bundle. We believe that it should be working, so Dumitrescu and Mulasse did some work already in this direction, which basically is working in the genus. It's not the genus which is important here. It will, where the dimension of the prime variety of your cover is vanishing. But we believe that it would be working. Also, you could have add some symmetries and things like that. We believe that it should be possible to quantize curve in C star square, so where you work with exponentiated variable. In which case, you see, so quantizing the x is okay. It's just multiplication by x, so when you take the exponential is nothing important. But when you quantize y, you would have exponential of h bar d over dx. And so, yeah, maybe I can ask a question. Does anybody know what this kind of operator is doing? Yeah, okay. So this is a shift operator. So what you would get would not be a differential equation anymore, but it would be a finite difference equation. Okay? So the belief is that, yeah, everything should flow. And actually, the structure of the proof for this general case is such that we have some good hope that just with a few complications because of technicalities, it should go through in the same way. Okay, yeah, another question?
Sorry, this one's just shorter. So the last bullet point basically is the conjecture is closed. So the
yeah, I mean, yeah, but yeah. Okay. We have a setup, so we've got some condition for this kind of curve such that we built a family of function solution to a differential equation of this type.
There's a notion of E has to be nice enough for...
Yeah.
Okay. But
so some of the constraint we did put was just for not having a paper which was too technical. Okay. So some of them can be relieved. Some other are a bit more complicated, but it's already very, very large.
Okay, thank you.
Okay. Okay, so that's it for the introduction. So now let's start the proof. So, yeah, so there will be an exercise session tomorrow morning. So since the proof is a bit technical in the sense that there are a lot of computation involved in the proof, but they are not that complicated, but it takes quite a lot of time. Some step of the proof will not be done today, but you will have to do it in the exercise session tomorrow. Okay? So let's start by just saying from what kind of spectral curve we start from for the topological recursion today. So I will just introduce the space of spectral curves, which I will consider today. So what I want today is that we start from hyperelliptic curves which are not ramified above poles. So what do I mean by that? Bertrand, can I erase that? Yeah. So I will start from equation of this type. Y squared is equal to Q of x, where Q of x is a rational function. I will be a bit restricted for Q of x, and this is just in order to avoid complicated notation for the lecture. In such a way that Q of x takes this form. It will have a pole when x goes to infinity. So there is a polynomial part. sum from k equals 0 to 2 times what I call R infinity minus 2 H infinity k x to the power k. So R infinity is related to the degree of the pole at infinity. And I will say that it might have poles at some other point, which I call lambda nu, for nu going from 1 to n, of respective degree 1 to 2 times R nu, H in H nu k divided by x minus lambda k to minus lambda nu to the power k. So here what I say is that I'm assuming that I've got even degrees for the, sorry? Okay. A lot bigger? Yeah. So k goes from 0 to 2 times R infinity minus 2. I call H infinity k the coefficient of x to the power k. Plus, and I allow poles at finite point. Nu is equal to 1, from 1 to n of degree up to 2 times R nu. And I call H nu k the coefficient of x minus lambda nu to the power k. Is it better? Okay. So what do I mean by, so hyperelliptic curve says that I've got an equation of this type, basically.
Can I ask you something?
Yep.
Just because I see that you are stopping that polynomial at an even order, are you thinking of Q of x as a determinant of some matrix which depends? Yeah.
Yeah. Yeah, but here it's just for the purpose of the lecture that I'm stopping at an even order. Because otherwise, so basically the idea is that I will have to introduce local coordinates above in x equals to infinity, and I don't want to have to deal with square roots. I think that Olivier might mention what happened in the case where it is odd. But so the fact that I've got even here and there, so I'm looking at some even order, means that my curve, because I've got y squared is equal to q of x, if you look at the x-plane, I've got infinity somewhere, and lambda 1 up to lambda n. Here I'm ramified, we're talking about that. And above infinity, I've got 2 points, which I will call infinity plus and infinity minus. Is it large enough? Yeah. So if I would have stopped at some odd order, it would mean that I would be ramified above infinity, and so these 2 points would be together. They would be a branch point. And above lambda I, so above lambda 1, I will call the 2 points above alpha 1 minus and alpha 1 plus. Alpha n minus alpha n. So the fact that I'm stopping here to even degree tells you that you've got 2 points in the fiber above each of these poles. Yeah? Sorry? Can you say again, do the lambdas have to be real? No, they don't have to be real. No. These are just arbitrary points in the complex plane. So what I will do, whatever happens, I will put a pole at infinity, and in some cases I will consider it as the unique pole when I'm setting n equals to 0. But if I want to have more than 1 pole, I will switch on the n. Yeah?
In the second
I will put the plus here. Yeah, sorry that the whiteboard is a bit small. So why do I put a 2 here? You will see it in a minute. The R nu and R infinity are related to the degree of the pole of y dx at these different points. And here it's a 0. Okay, any more questions? Okay, 2 questions there. Olivier? Wait. No.
Okay, so if you think about that curve from matrix model point of view,
Yeah.
I think the potential is some polynomial plus log potential. Is that correct to think in that way?
Plus,
Some
yeah,
log terms.
yeah, you could have log terms, yeah.
Okay, so then that's the space you want to think of.
Sorry?
Is that the space you want to think? So can I think that basically you want to think of space of those potential and what kind of freedom you have?
You could think of it from this point of view if it's better for you.
Okay, so in
Here,
that
I think of it arbitrarily just from a space of spectral curve point of view.
I'm fine with that. But then in that, at least, okay, if I think of that from matrix model point of view, then I have to think about, for example, the fitting fractions.
Yeah.
And do you think about that fact as well?
So I will talk about it
Okay.
just after.
Sorry, yeah, thanks.
So here you see, I'm not talking about the one form y dx. I'm talking about the function y square. So it's not exactly the same information that you get from the potential in the matrix model. I mean, not directly. Okay? But you will see it in a second.
It was just a question about the minus plus. It's just arbitrary
Yeah.
over each point.
Yeah,
There's
it's
no
an arbitrary
global-
labeling. So everything will be independent of this labeling in some sense. Let's say I start from the beginning by saying, okay, this is the plus sheet of my cover and this is the minus one. Okay? Okay, so here I fixed my hyperelliptic curve, so I could think of the space of Q of x or the space of H here as being a space of hyperelliptic curve. Yeah, just to mention here, the one way to think about that is to think of Q of x times dx squared as a quadratic differential defined on the base curve. And so you could put some Poisson structures there, and the notation H come from there. I mean, these are Hamiltonian related to the corresponding system. Okay, and so this is indeed the Poisson structure which is interesting for us. Now, this is from the perspective of Q of x, but so if Q of x takes this form, what happens for the one form y dx? What I did here is kind of fixing the singular part of y dx. It means that y dx has poles at, so we've got two different kind of poles. It has poles at infinity plus, infinity minus, and the alpha I plus and alpha I minus. And the shape of the expansion around these poles is fixed by the shape of Q of x. So around alpha nu plus or minus, one has the following behavior for y dx. So you can read it from there. Take the form sum k going from 1 to r nu, x minus lambda nu to the power k dx. And here, the coefficient, I will call it t nu k. And alpha plus and alpha minus, they correspond to the value of y dx in the two different sheets of the cover. And so y in one is related to the value of y in the other one just by a change of sign. Because we've got an equation of the type y squared is equal to q of x. When you fix the value of x, you fix the right-hand side. And so there are two values for y which fit, one differing just by a sign. So the expansion are on plus and alpha plus and alpha minus. They just differ by a sign. And then you have something which is holomorphic around this point. Okay? This is more related to the potential of the matrix model. Now, around infinity plus and minus, we have a similar expansion. We have a sum from k going from 0 to, yep.
Read what is in the
Sorry?
order of...
O of dx. Yeah, so I'm considering a 1 from y dx, not the function y. K going from 1 to r infinity, t infinity k, x to the power k minus 2, dx. And I've got something which is of order O x minus 2 dx. And here I choose just for the notation a minus plus sign, because when we take, I want to extract these t's, this coefficient, by taking residue, and when I'm taking a residue at infinity, I get a minus sign. So it's just for simplifying the notation later. So you see that there is a shift by minus 2 here. Some people might wonder why it is there. I've got the 1 from y dx. Dx has a pole at infinity, actually. So in order to have something which is regular, you should consider d of a local variable, which would be x minus 1 here. So it gives you dx over x squared. And that's why I've got this O here, which is regular. OK? Now, going back to your question. Let's say I give you Sel's expansion. So I give you the t's here and the t's there. Is it enough in order to fix y dx? The answer is no. Because, I mean, in general, it is no. If I would have a genus 0 curve, so if y dx was living on the sphere, I would have, for y of x, let's say, I would have a rational function. I know its poles. I know its expansion around its poles. So I could do a decomposition of this function as a rational function, and this is enough in order to get it. But here I've got an higher genus curve, meaning that if I fix the pole structure, I can always add some holomorphic form to it. I will not change this formulae, but I will change the one form. So in order to fix y dx completely, I will have to fix also its holomorphic part. So there are different ways to do it. What we will do here is by fixing the periods of y dx along some basis of cycle. So for this, in order to do that, we just consider we pick an arbitrary basis, AI, BI, I ranging from 1 to G. Of H1 of sigma. So sigma, I think I didn't say it before. What I call sigma is the algebraic curve defined by the equation y squared is equal to q of x, z. So here, G is the genus of my curve. So if I would have a genus 0 curve, this would be dimension 0. So I don't have any any cycle I could choose here. And this corresponds to the fact that the space of holomorphic differential is a point. So I cannot shift anything here. Now, here I can shift by holomorphic forms. So in order to do that, to know how I define it, I fix a basis of H1 such that AI intersection with Pj is delta Ij. And we call filling fractions the periods along the A cycles. So for I in the set 1G, I take the periods along AI of y dx, and I call it epsilon I. Okay? Now, if I give you the t's, so the coefficient of the expansion around each poles of y dx, and the periods, now it fixes y dx uniquely. Yeah.
Don't you have to take the relative homology with respect to the poles, because you might have residues at this point taking integrals? So
With
when you
relative
integrate,
to the poles? No, I don't have to do that. Why?
y dx might have. Oh,
Sorry?
y dx might have poles, right?
Yeah, y dx has poles at infinity plus minus and alpha plus minus.
So depending whether your cycle surrounds poles or not.
Yeah, it's a different basis.
uh,
If you move it, you get a different basis, that's all.
But yeah, it's the same curve of homotopy if you move a pole from inside and outside.
It just gives you a different set of coordinates if you move it. Yeah, Bertrand maybe wants to.
In fact, I think this is H1 of sigma or sigma minus pole Z, no? Yes.
Yeah, okay. I thought you were talking about relative to the poles, meaning, okay. So let's call P, where P is equal to the set okay? Yeah, because they are inside. Yeah. Okay. Now, just a remark. So first, I presented the space of curve being given by the H over there, the coefficient of Q. Here, I'm saying, okay, now what I could consider is the space of y dx given by these t's and epsilon. How are the two related? I mean, if I fix y dx, it means that I'm fixing y, and so I'm fixing y squared. Now, what you can see is that if you look at the expansion of y squared around one of its poles, you will get something of this form. So let's say you take the expansion of y squared around infinity in terms of the t's, you get a polynomial part. What you will find out is that the first coefficient will just depend on the t's and not the epsilon. I mean, so you can write it explicitly in terms of the t's. But some of the h here, for k being lower, they will depend on the part which is hidden there. Yeah?
Can you be more precise about the choice of basis for H1? Because you said you impose this condition intersection of A's and B's. And also the A's don't intersect.
Can you speak a bit louder?
So can you be more precise about your choice of basis of H1 of the punctured sigma?
I just choose one, arbitrary.
But you have A's and B's, right?
Yeah.
These are, they generate H1 of the unpunctured sigma, right?
Yeah, yeah, okay.
But then also
No,
the
I
A's
think-
and the A's.
I think we don't have to remove the poles.
The A's with
Yeah, no,
themselves
no,
don't
I don't see-
intersect. You did not write that equation,
I mean,
and the B's also.
You can do, yeah, otherwise you would have something, yeah, no, you don't need it. If you would have, so let me draw it. I've got my curve here. I've got a bunch of poles here. What I need is just a basis of this type.
Right. Which means that also the A's don't intersect and the B's don't intersect among themselves.
Sorry? So,
Yeah.
What I'm saying is that so I pick one. I don't care whether the poles are inside or outside. If I changing it, will change the value of the epsilon. That's all.
Okay. So there's going to be A's and B's and the other elements that circle around the...
Yeah, it gives you a basis of H1 of sigma
then
minus P.
And then the A's and B's are a symplectic basis for the unpunctured sigma.
Yeah.
This is what, okay.
And so that's the only thing I needed here in order to define the filling fraction. Now later on, if you want to follow the proof to the end, you would have to introduce the basis of H1 of sigma minus P. But for what we're doing here, just for the filling fraction, you don't need it. What will happen is that, okay, the epsilon I, the filling fractions themselves, their value, they depend on the choice of basis you take. Okay? If you change it, you will change the epsilon. But the one from y dx doesn't change. Is it more clear? Okay, so I will keep that. Now, yeah, what I was saying is that fixing the t's, it doesn't fix the one from y dx completely, but it fixes part of the h, just the higher order one. And so let's see it here in an example. Yeah. Okay. Yeah. Okay. Yeah, no, sorry. I just come back to the question. So I agree there should be the sigma minus P because otherwise you would have you would change the value of the epsilon 1 if you go from one pole to the if you go around one of the pole because you might have non-vanishing residue here. Okay. So we are there, and so let me give an example. So we'll take the example where n is equal to 0 there, meaning that I don't have any poles away from infinity. So I get q of x, which is a polynomial. And I want it to be a polynomial of degree 4. So I take R infinity is equal to 4. So that R infinity minus 2 is equal to 2, and 2 times 2 is equal to 4. So what I get is something of this form, this one. It means that y dx, it has an expansion of this type. So you start with t infinity 4 x to the power 2 dx minus plus t infinity 3 x dx minus plus t infinity 2 dx minus plus t infinity 1 dx over x plus O of dx over x squared. So I am just taking this formula with R infinity is equal to 4. Now, what is the spectral curve corresponding to this case? So I can look at the expansion of y squared around infinity. So in this case, I just have one pole, meaning that q of x should be a polynomial of degree 4. So I just have to compute the polynomial part of y squared. So I get y squared is equal to t infinity 4 squared x to the power 4 plus, and then I get 2 times t infinity 3 t infinity 4 times x cubed plus t infinity 3 squared plus 2 times t infinity 2, t infinity 4 times x to the square plus, now for x, I get 2 times t infinity 1, t infinity 4 plus 2 times t infinity 2, t infinity 3 times x. And now let's say that I want to see the constant term. I will get contribution from t infinity 1 times t infinity 3. Okay, I can express it in terms of the t's. T infinity t2 square, okay? But t infinity 4 has to be, might be multiplied by the coefficient here. And I cannot express it in terms of the t's. So I've got one coefficient, the constant coefficient, which I call h0, which I cannot express just in terms of the t's. So there is one coefficient to be fixed. But now if I look at this curve, this is a double cover of P1 of degree 4. So you can think of it as being ramified at 4 points. So let's take a simple picture of this type. If you look at it, it means that you get a genus 1 curve. So the genus is equal to the number of coefficients I'm missing here. And you see that it is equal to the number of epsilon as well. So in general, and you will prove it in the exercise session, what you will have is that in this coefficient here, you've got many of them which are fixed by the t's, and you will be missing g of them, where g is the genus of the curve. Yeah?
So if I were to think in the terms of, say, I take a spectral curve of that form, for me it arises, as you know very well, in the theory of Pan-Levé equations, right?
Yeah.
So when this H0, you're thinking of it as fixed by the accessory parameters.
By the?
So-called accessory parameters.
What do you call accessories?
Okay, so the coordinates of the actual solution of Pan-Levé. So Q and P.
Yeah, sure.
Yeah, okay.
So here I took it as an example because at the end of the day, you will get Pan-Levé 2 equations here. And yeah, that's exactly the perspective we took, actually. The way we obtained a representation which seems to be good for us in order to derive the proof was coming from the study of Pan-Levé equation. Okay, so what you will find out in general is that some of the h will be fixed by the t's. They would correspond to Casimirs when you think of the integrable system. When you fix your Casimir, it means that you're choosing a symplectic leaf, let's say, in the space of quadratic differential. You have a symplectic structure, and the symplectic space will be basically of dimension 2g, where g is the genus of the curve. And so the missing coefficient here will be Hamiltonian, corresponding to flows in this space. Just something I don't know. Bertrand, did you talk about the Newton polytope? No? Just want to mention a way to obtain the genus of a curve of this type. A recipe which might be useful sometimes, which will show you. So in the case of a hyperelliptic curve, it's not very hard to find the genus, but sometimes it's a bit more tricky, and there is a very simple way to do it. Which is by writing the Newton polytope. So if you start from some E of xy of this form, and you wonder what is the genus of the curve defined by E of xy equals to 0. One way to get it quite fast in a generic case, so for generic value of the alphas here, is by drawing the Newton polytope. So you draw some integer lattice. In this direction, you will think of it as being the degree of x. here the degree of y. Whenever you've got some alpha ij, which is non-vanishing in your equation, you put a dot at the position aj in your lattice. So for example, here I've got an equation which is y squared is equal to a polynomial of degree 4. So I've got alpha 0, 2, which is non-vanishing here. And I've got all the x, which are non-vanishing here. When I've done that, I draw the polytope here, up, obtained. And I look inside, and I count the number of points, integer points inside the polytope. So here, sorry, yeah, I had one more. So 0, 1, 2. And here what you will get is that you just have 1 point, which is inside. Okay? Just the point 1, 1. The number of points which is inside the polytope is for generic value of alpha I, the genus of the curves that you're considering. So in this case, it's very easy. I just have 1, so I've got the genus 1 curve. Yeah? Sorry?
Sorry, if you consider the degree of the polynomial, you can find easily also the genus, right?
Yeah, I mean, for me, it's a very simple way to say it. Bertrand, you wanted to say something? Yeah. Okay. So up to 1050, that's right?
Sorry, the chat is a little down there. So normally you should finish at 10:50, but we started a little bit late, so.
Okay. Let's say 10:55. I mean, there will be a break after. Okay. Now, up to now, I just looked at the spectral curve and nothing else. I didn't talk about topological recursion. So what I want to do is to define and use the topological recursion for this kind of spectral curve. So I'm starting from y squared is equal to q of x. And what I do is that I define omega 0, 1 as the one form y dx. For defining the topological recursion, I don't need only omega 0, 1 or the equation of the spectral curve, but I need also omega 0, 2. In order to define omega 0, 2, there are many ways to make a choice, but what I will do here is that I fix a basis of, and no, it's a basis of H1 sigma z, which I call AIBI. And I just, yeah, I should take the same one, sorry. So I will pick the same one as I did there. And what I will do is that I will enforce my one form, my two form omega 0, 2, to a vanishing period along the A cycle. So omega 0, 2 is defined by the fact that I think that you've seen that many times now after this week. Omega 0, 2 is defined as being a differential in sigma squared with poles only on the diagonal without residue, with a double pole, and with a coefficient which is fixed. So it fixes the pole structure of omega 0, 2. Now you need to fix also its holomorphic part, let's say, and we do that by fixing that the A period along a given and chosen basis are vanishing. If you do that, omega 0, 2 is fixed, okay? If we would have a genus 0 curve, we wouldn't have to make such a choice. It means that here, everything would be fixed basically by the equation of the spectral curve. Now, if I do that, if I take n greater or equal to 1 and h 2h minus 2 plus n greater or equal to 1, I define omega h n. Let me know if it's too small again. So I will define by induction some omega hn, which are n form on sigma to the power n, by the following recursion formula. You take all the ramification points. So in this case, for example, you've got 4 of them. So what I call R is the set of ramification points. Yeah.
Could I quickly ask, so omega 0 is determined by, it has to have double poles along the diagonal?
Yeah.
Then it has to have this vanishing condition on the integral and nothing else?
Nothing. So we have to be more precise. You need to have that on the diagonal in any local coordinate. It behaves like dz1, dz2, z1 minus z2 square plus holomorphic. Okay? So you fix the coefficient here as well.
Okay, and then the second condition is some condition on the holomorphic part?
Yeah, because if I just give you that, once again, you could shift it by some holomorphic form. Actually, you could shift it, you see, by a product of holomorphic form, holomorphic form in Z1 and Z2. So the dimension of shift is quite big. So, but here, just by fixing that, I fix completely all of this.
Okay, thank you.
Yeah.
Is there a typo? You're going from Z1 to Zn, I suppose?
Yeah, there is. Thank you. So R is the set of branch points, sorry. Branch points. Okay. So yeah, I will write it here. And maybe I will leave the formula here. So we've got omega hn of z1 up to zn, which is the sum over p being a branch point. I consider the residue when z goes to p. So I take the residue at all the branch points of the following thing. First, I use a recursion kernel. So I take omega 0, 2. So it's a form in 2 variables. So the first one is z1, and the second one is integrated from sigma of z to z, where I will write it here. Sigma is the hyper-elliptic involution. So basically, it tells you that x of sigma of z is equal to x of z. So x is fixed by sigma, but y changes sign. So if you consider your equation here, sigma changes the branch of solution you consider. So you exchange the two shades. Yeah? Sorry? Yeah? Yeah, in this case, yes. In general, it is not. That's why the hyperelliptic case is easier to present and deal with.
And in omega 02, you have Z1.
Yeah, the same one as here. And so the second one is from sigma of z to z, where z is the point you use for the residue. And you take the difference between omega 0,1 of z minus omega 0,1 of sigma of z. Up, and one more. You see that in this case, omega 0,1 is y dx, and y changes sign. So here I could replace it by 4 times y of z dx of z. No, it's not all. So it's an induction on h and n. And so we multiply it by a formula which recovers the drawing which was on the left blackboard when you arrive. First, you decrease the genus h by 1 and increase n by 1. And you evaluate it at z sigma of z, z2 up to zn. So I guess you've seen, I mean, everybody has seen this formula already, right? Hope so.
You need to write it again, because not everybody was here last week.
Okay, and then we make a sum of this type. We take a partition of the set z2 to zn. We cut h into 2 parts, h1 and h2. And we basically distribute h and the variable here, I mean z2 to zn, except by removing z1, into 2 parts, into 2 omegas. The first with a genus h1, a plus 1, and with the first argument z, and the second one is genus h2, b plus 1, sigma of z, b. Now, let's say that I give you this formula, and here I could have, let's say, h1 is equal to 0 and a be empty. This would give me here some omega 0,1 and here some omega hn. This would be an issue because this is what I want to use to define that. So I've got to remove that. So I want to impose the cardinal of a h is not in the set, so 0, 0, neither in the set, so it would be n minus 1 and h.
So you're excluding omega 01 and omega 02 from the set.
Sorry?
You are excluding omega 01 and omega 02.
No, omega 02 is still there.
Okay, so you just exclude omega 01.
Yeah. Because you see, if I've got some omega 02 here, if I've got omega 02 here, it means that I've got a variable here. Here the genus would be h, and here I would have one less variable compared to what I have here. So it's okay. But later I will remove omega 02 as well. Okay, so that's the definition that we use for the topological recursion. No, this is valid only for n greater or equal to 1. So you need at least one variable. So you will have a 1 form. But we can define it also for n is equal to 0. So I will not give you all the formulae, but I will give you a formula for h greater or equal to 2. We can define some omega h0, which is now just a number. And it's 1 over 2 minus 2h, sum over p range point. Yeah, it's going to be too small again. 1 over 2 minus 2h residue sum over P branch point residue when Z goes to P of, and you take omega H1, so you add 1 point, Z, and you integrate y dx, yeah, I didn't, or omega 0, 1 from a reference point O to Z. So a priori, this would depend on the base points that you take, but because of some property of the omega H, one of which you will prove in the exercise session, omega H do not have any residue at the branch point, so that when you change the base point, it doesn't change the residue here. Okay?
So that's omega 0, 1 on the right.
Omega H1 and omega 0, 1 here, if you wish. Yeah. So there exists formula for H equal to 1 and 0, but they are a bit more complicated, so I don't want to write them here. Okay. So we've got basically omega Hn for arbitrary value of H and N starting from 0. And out of that, we want to build a wave function. But before going there, I want to introduce some property for this differential form omega, which I will call sometime correlation function because of their origin in the matrix model setup. So I want to introduce some variational formula which study the following question. What happens if I change the value of the t's? How does it impact the omega Hn? And there is a nice way to obtain it in general. So the t's here, they are obtained by considering residue at the poles of y dx. So they are residue of something. In such a case, we have shown that the topological recursion produces correlation function such that the derivative of the omega Hn with respect to these times, computed as residue, can be themselves written as residues. So I will write the resulting formula in this case. So for H greater or equal to, for K greater or equal to 2, the omega Hn over dt infinity K, I want to compute that. So the recipe is usually is that if this t is given by a residue, let's say at infinity, then d omega Hn over dt will be given by a residue along some dual cycle of omega Hn plus 1. So here I would have omega Hn of, let's say,